All right, in this video, we're going to learn how to evaluate the null hypothesis. And we're going to use an example from prior videos in which we're comparing test performance on exams in classes, traditional classes in statistics versus classes that utilized online videos. And if you recall, the population mean was 78.13 for the traditional classes with a standard deviation of 8.24. The sample had a sample mean of 81.22 with a standard deviation of 7.34, and there were 36 students involved. So those are the numbers, and we found that there was a Z corresponding to 2.56. And if you have any question about how this was all conducted, go back and watch the prior video. But anyways, that's what we're working with right now. We have a Z of 2.56, but we really could not conclude that the sample mean was reliably different from the population mean because we didn't have a cutoff criterion. We needed something to tell us whether or not that result was so unusual that we'd be unlikely to conclude it could have been drawn from the sampling distribution represented by the null hypothesis. Okay, so that's where alpha comes in. And alpha is our decision-making criterion. And it really helps us answer the question, what constitutes a result that is so unlikely to occur by chance, and by chance we mean sampling error, that it is enough for a researcher to reject the null hypothesis? Okay, so we need to set something called the alpha level. It's really developed by custom. It's under the researcher's control. It does not change. And it's determined in advance of running the statistical analysis. So this is something that's done early on before we ever start analyzing the data. And we need a criterion that's strict enough that it is unlikely that a given result, for example, we're looking at a Z-score for a sample mean right now, that the result that we ended up computing and finding would be observed due to sampling error in the sampling distribution. The reason is you don't want to conclude, for example, that say an intervention or some manipulation of the independent variable had a true effect if it's possible or even likely that any difference between the sample mean and the population mean was simply due to sampling error. That wouldn't make any sense, right? Because those are just chance factors. So by custom, statisticians have determined that, hey, it seems reasonably conservative to say that there's only a 5% chance, or proportionally 0.05, 5% chance that the result could be obtained due to sampling error. So when we say alpha equals 0.05, what we mean is that there is a 5% chance or less that the observed result is due to sampling error or chance factors. Now, if the result has a less than 5% chance of occurring because of sampling error, then we necessarily conclude that the result falls within something called the region of rejection. And that rejection is an important word because what we end up doing then is rejecting the null hypothesis. So our alpha is set in advance, and if we get a result that convinces us that it's unlikely that the sample mean could have been drawn from the sampling distribution represented by the null hypothesis, that there was a less than a 5% chance of that occurring, then we reject the null hypothesis. Okay, so then the question becomes, well, how do we determine the cut points in the sampling distribution that accounts for a total of 5% of the area under the curve of the sampling distribution? So it sounds like a thorny problem, but it's really pretty straightforward how to do this. So here's our sampling distribution. Now, keep in mind, this is the sampling distribution, assuming that the null hypothesis is true, right? So we have the standard error of the mean right here, right? And if our z-score equals 0, what that would mean is that the sample mean was exactly equal to the population mean. And that's how you would end up with a z-score of 0. And as you get further into the tails of the sampling distribution, either on the negative or the positive side, what you're essentially saying is that the sample mean is looking increasingly different from the population mean. Okay, so the question really is, look, if we want if we want it to be just a 5% chance that we are observing the result due to sampling error, then we have to identify the amount of area under the curve on both sides of this distribution that corresponds to a total of 5%, okay, or 0.05, okay? So that the question is, all right, if we're going to have a cut point, which is going to be right here, okay, what is the corresponding z-score that allows us to put 0.025 in one tail and 0.025 in the other tail? Because when you add those together, you get 0.05. That just means that 2.5% of the area under the curve is represented on between both sides, both tails of the sampling distribution. Okay, so what is the z-score that corresponds to 0.025 on both sides? Okay, so to do that, we need to look at a z-table. Now, I'm going to put up a z-table here that I found online, but every textbook has a z-table that is similar to this. So you'll just have to look in your own textbook for the right table. But basically, you're going to look for a table that, in the columns, that identify the amount of area in the tail, okay? And if we assume that the totality of possible results in the sampling distribution corresponds to 1.0, meaning everything is accounted for with the value of 1.0, then we want to locate the size of this shaded region right here that equals 0.025, okay? Now, the good news is once we find it for one side, it's going to hold for the other side of the sampling distribution as well, because we know that the normal distribution is symmetrical, right? So if we subtract 0.025 from 1.0, we get 0.9750, okay? That's when we need to now look at the z-table. So we look at the z-table and we say, okay, what we've got to find in here in all this mess of numbers, right, is we've got to find this value, 0.9750. Now, where does that occur? Well, it's right there, right? So there's our value in the z-table. So what does that value then correspond to in terms of z-scores? Well, we look over here in the row and we get 1.9, okay, and that takes us out to the tenths. And then we look here in the column to get the hundredths, and that's 0.06. So in other words, the z-value that we are now interested in is 1.96, right? And because it's going to be on both sides of the distribution, our cutoff will be on both sides as well. So it's going to be plus or minus 1.96. Okay, so now we have our cut points. We have a cut point on the negative side and a cut point on the positive side. And the reason we need the two cut points is because we don't really know, prior to the experiment, whether or not the intervention is going to have an effect, whether or not students learn better using the online videos or not. Maybe they ended up doing not as well on the exam. So we'd have to have cut points on both sides. So this is what we call a two-tailed test. We'll be talking more about that later in another video, but the cut points are on both sides. And if the sample mean, as represented by the z-score that we calculated, if that were to fall in either of these shaded regions, we would say that the result was in the region of rejection. Now, where was it? Well, it was right there. Remember that we had calculated a z of 2.56. If we were to locate this in the sampling distribution, it comes out right about here. Well, you'll notice that it's in the shaded area. So we would conclude that it is in the region of rejection, and therefore we would reject the null hypothesis. Now, if the z-score had been smaller, let's say the z-score had been like 0.5, right, positive 0.5, and we would locate it right here, then we would fail to reject the null hypothesis, and our conclusion would be different. So again, remember, rejecting the null hypothesis, failing to reject the null hypothesis, those are mutually exclusive decisions. You can only do one or the other. So what does it mean to reject the null hypothesis? Well, what we're saying is that the observed result, the z-score that we calculated for the sample mean, is unlikely to be due to sampling error. Okay, its location in the sampling distribution is just so far off in the tail that it's unlikely to be due to chance. And the likelihood that we would obtain the result due to sampling error is less than 5 in 100. Therefore, we reject the null hypothesis that the sample mean is equal to the population mean. And because the null hypothesis and the alternative hypothesis are mutually exclusive, you can have one or the other, therefore we're going to accept the alternative hypothesis. And that decision implies that the sample was drawn from a different population than the one represented by the null hypothesis. There's something different about it. So in our example, it does provide evidence that the test performance of students who completed the online videos was reliably different from the test performance of students who were in a traditional classroom. You know, that's really kind of saying the same thing as there is a relationship between the independent variable and the dependent variable. In other words, it did kind of matter what class you were in. Okay, and there is a relationship in test scores. Those test scores seem to increase in association with being in the online video class condition. Now, let's distinguish very quickly between the alpha level and the p-value, and we'll be talking more about p-value later, but it's good to just sort of, discuss it quickly here. The alpha level only refers to the size of the region of rejection. It's under the researcher's control. It's determined prior to running the analysis, and it doesn't change. Now, the custom has been to set it at 0.05, although there may be some good reasons to set it at a different level, at 0.1 or 0.01, really depending on the nature of the experiment. But usually what you'll see is that it's set at 0.05. So when we run the experiment and we run our analysis, that's where the cut point tends to be, is at 0.05. The p-value, on the other hand, is the probability value. Now, this is determined during the statistical analysis. In other words, we can't know the p-value until we've collected data and run our analysis. And the p-value refers to the exact likelihood of obtaining a result due to sampling error. Now, for experimental purposes in demonstrating a relationship between two variables, we would like to see the p-value be pretty small. But most importantly, it's not under the experimenter's control like the alpha level is. The alpha level is something we set prior to running our analysis. But the p-value is something that we discover once we run our analyses. And again, like I said, smaller p-values mean a greater chance of rejecting the null hypothesis. So alpha level and p-values, they're not the same thing, but they're easy to confuse. Now, some good news is that statistical programs report the p-value for you. You typically don't have to calculate that on your own. It's not hard to do. You just use a z-table. But no psychologist does that, anymore. I mean, the stats programs will report p-values during their analyses. Okay, so big picture, alpha defines the size of the region of rejection. If the observed statistical result, in other words, a z-score for a sample mean, falls within the region of rejection, we reject the null hypothesis. In other words, we reject H sub 0. Rejecting the null hypothesis means accepting the alternative hypothesis. That's our research hypothesis, and that's sort of the hypothesis of the most interest to us. And the p-value tells us the exact probability of observing the statistical result due to sampling error, in other words, chance factors. And again, always remember, the alpha level is something that we set, and that's different from the p-value, which we determined via our analysis. All right, next up, type 1 and type 2 error.